now. And so we have that happening, and Linda log this. Okay, so I started talking, and I think we're in good shape. I think you should realize that really we don't have a lot of time left, but that's all right because we've made a lot of progress. We are on time and on schedule, and soon after and on the week of Thanksgiving, we'll meet on Monday, but not on Wednesday. And then we will be taking the Wednesday off, but there will be the videos and things like that. And my daughter's getting extension cords, so we don't have the.
It looks like it's good to go.
Don't have a power outage here, so maybe we'll see how that. Oh, you think it's good to go upstairs?
It's on your login page.
Okay, so I'm just going to stay here. I'm not going to make people shut down while I go to another room. Okay, Linda, do you have anything to share with the students?
Not especially. We did go over some study tips in the guided study group today. So I do want to remind everyone to keep track of the variables that we've been using, as well as the units that go with each one. That's going to be really helpful in trying to figure out which equations you're using. So making some kind of cheat sheet for yourself to reference now instead of waiting until finals week is going to help you out quite a bit.
Okay, that's good. Anything else, Linda?
Nope, that's all I got.
Okay, great. I'm throwing it open for students. If anybody has any comments or questions, this is a good time to ask them. Your questions are always welcome. My daughter did get power into here, so we should at least have a power outage. So I guess I'm going to ask, okay, so Monica has her hand up. And Monica, what is your question?
I noticed I'm not able to upload the PDF for LSA P4. It's not on my Blackboard.
Well, I'll check and see, but I'm not going to, take time out from the lecture to go and do that. But I will go check. And some of the LSAs, the most recent ones, I'm still in the process of establishing a place for those to be. So, and Linda, you will be happy to know that my daughter's dog is visiting our class too right now. So I'm going this. So we almost have a. Yeah, in fact, both of her dogs. She has two dogs. Okay, they're going upstairs. So, okay, anything else, Monica? Or not Monica? Well, anything else? Anybody? Okay, well, we'll assume that's good. Your questions, of course, are always welcome. And Linda and I have office hours and, GSGs and things like that. So we're going to go into some content now. And Linda, one thing that I think would be useful, and I do realize that you're going to be, leaving us in a bit for, your other appointments. But could you show the students, please, how they can use a calculator to find logarithms?
I absolutely can. Would you like for me to do that now?
I would.
Okay.
And the reason Linda's doing this is because tonight we will have to use logarithms with the calculators to find answers. So she's going to show you that.
All right, so I'm just opening the calculator app on my computer. So if I'm trying to find the log of something, now we do have two different logs available. There's a log base 10, which is this button that I'm looking at right now. And there's also a log base E, which is also referred to as the natural log. So it is something that exists, but for this course, you guys will not need to use that. So if I'm using the log base 10, then really this works very similar to how your trig functions worked. So for example, I can type in 100, and then if I hit the log button, then it takes the log of 100. And you can see that up here. It's going to show you exactly how to figure out what it actually computed. So if something is typed in incorrectly, then you'll know.
Okay, so it is important that you know how to use the logarithm button or calculator, because that's how you'll get some of the answers. Okay, so that is good. And Linda, if we can jump back to the PowerPoint slide then. And Linda, I'm going to suggest, just in the interest of time, that we move directly to the, and I'm going to call it the bird problem, but I think you know what I'm talking about. There is a slide there.
Yep.
That has that. And so we're going to jump directly into this problem. Now, when we're doing this problem, there is going to be a lot of learning and things like that will happen, but we're going to start and we're going to be using that decibel equation that I introduced last time. So we are going to be talking about that, and you know, that's what we're going to have here. So now what I'm going to do is I'm going to read this to you, and I'm looking at a really tiny screen, so this is hard to read, but I think I'll get it done. So what you got, in fact, I'm not going to read it. I'm just going to talk to you about it. Okay, so you got a bird there sitting, and the bird is singing a song. And you can see that there's like little musical notes coming out from the bird's mouth. And you got a guy that's standing over here at a point that is called P1. And you have the same guy that is standing at point P2. Now, please do not think that, oh, a guy can be in two places at once. That is physically not possible. But here's what we're doing. So we're talking about that the sound is being emitted by a singing bird. And the bird acts as a point source of sound. That means that out of the bird's mouth is coming the sound, and that is 1 point in three-dimensional space. And I did talk about the way the sound waves happen, and they will go out in, I'm going to use the word concentric spheres, but they'll go out in all directions. Now, you all know that the closer you are to the bird, the louder you hear the bird, and that's what these equations actually are about. So then what it says is, so assume the bird is a point source, and the bird sings with constant power. So you can think about this bird just hitting a long note at the constant power. And by the way, we talked about what power was too. And so the intensity is given by an equation. And the equation, and we talked about this last time, the equation is, and I'm going to try something that I don't know if it will work or not, but my daughter's PC, which is the one I'm being forced to use, does have a stylus. And I'm going to see if I can actually write on here with a stylus, and that might not work, but I'm going to try it anyway. Okay, so the intensity, and of course that didn't show up, so that's not going to work. So I'm going to go up here and get the little pencil.
Yeah, once you have the pen tool selected, then it should work with the stylus though.
Really? Okay, I will try that, Linda, because that would be actually good. Okay, so I'm going to try the stylus then. This is not my PC, this is my daughter's PC. Okay, so we learned that the intensity, and that didn't show up either. So maybe I need to pick the color too, to be black.
Yeah, you have to select the color.
I did. Okay, so now I'm going to see if I can write again. This is my third try, and this is the last try. But we learned that the intensity in this stylus doesn't work. Okay, it said, I don't know, create a QR page for this thing. Okay, so that's not working. So I will try just to draw this way. Okay. So what happened is the equation that we're looking at is, and Linda, is it like super difficult to bounce back and forth between the whiteboard and this?
No, it's
For
not
you?
too bad.
Okay, I'm going to ask you to do that. So go to a whiteboard and I'll just write on a whiteboard. Okay, so we're trying that again. Okay, and I don't think the stylus thing is going to work, but I'm going to maybe try that and just see. Okay, so the intensity, and again, that doesn't show up, so I have to just use my finger. So the intensity is equal to, and this is what we learned last time, is the power over 4 pi r squared. So this is the intensity that we're going to have, and this is the equation that we're going to use for the intensity. Now this depends on the radius of the sphere, and that's the surface of area of the sphere. So this is going to be in units. Linda talked about units being important. They are. This is going to be watts over, and this could be square meters. Okay, so we'll have that, or it could be some other dimension. But anyway, we're going to be using this because this is how intensity comes. And so it's watts per square meter. Okay, so that's what's going to happen. Another formula that we learned was last time was that beta, which is in dBs, is 10. They put the dB here like that. And then this is the log, and there's where the log comes in. And this is log, and let me see if I can change this to the eraser. In fact, I think what I'm going to do is I'm going to erase the whole thing. I'll hit this trash can that I've learned how to use. Okay, so here's the other equation that we have, and I have to go get my pencil again because I have to keep refreshing that. So I'm going to be drawing again. This is the other equation that we're going to be using. And this is beta, which is going to be 10, and this is dB. And dB is a unit that stands for decibel. And this is going to be log, and this is log of the intensity, which is I, over the log of, or over I0, where I0 is a reference intensity, and we talked about that being the threshold of hearing. Okay, so this is the equation that we have for the intensity. Now, I hope you guys wrote those two equations down because you're going to see them on Linda's chart very soon. And we're going to talk through this. And I want you to understand this because this is actually a very good example. And if you really understand this example, you can do the LSA that I asked you about on that. Okay, so Linda, let's please, I'm erasing this, but now I'm asking Linda to please go back to the slideshow. Okay, so we got this bird and it's singing, and what they want us to say is by how many dB does the sound intensity drop if you were to move from point 1 to a point twice as far from the bird. So what you're saying is what's the dB? How many dBs does the sound intensity level drop when you move to a point twice as far? So you see, here's what's happening. P2 is twice as far from the bird as P1. Now I want to pause here just for a second for people to maybe if they want to ask questions about what's going on. So you got this bird that's a point source. We're going to be using that one equation about the intensity equaling P over 4 pi r squared because this is going out in spherical things. And we're going to be using the dB equation, which says that beta is equal to 10 dB times the logarithm of I, where I is the intensity, divided by I0, which is the reference intensity. Okay, so I'm pausing here for a second in case anybody wants to ask a question right now. So it looks like Amber's asking a question. Go ahead, Amber.
So I know this is kind of jumping ahead, but I'm just wondering if the log equation is what shows the intensity dropping. Is that what we're using the log for?
I think, Amber, and I'm not trying to be rude with this, but I think that it measures the, I'm going to answer your question, but I think the best answer, or the most complete answer, is when we start looking at the problem. And so what this is going to be is, and by the way, I did lecture on this problem in the videos that I posted. But anyway, so what's going to happen is it really is a relative intensity because it's the ratio, Amber, of I, the intensity divided by I0. And you're going to see that when we go to the actual solution itself. So I gave you an answer. It might not have been a complete answer, but I'm just going to say hang with it, okay?
Okay.
All right, so let's advance the slide, please, Linda. And I think this actually might be a touch screen thing with my daughter, so maybe I can go down and I'll try to do that sometimes. Okay, so here's what we're going to do. Now, we ask about the difference in intensity. And so this is going to be, we want to be looking at beta 2 minus beta 1. Now, beta 2 is when we are twice as far from the bird as we were to start with, and beta 1 is when we were at the beginning distance from the bird. Okay, so what's going to happen then is, and Linda, I'm almost thinking it would be good, and Linda, I'm sorry I'm giving you so many of these logistical directions, but I think we may want to go back to, or in fact, maybe, let's see, I have to try to share screen. So can you go to the, and Linda, before you leave, we'll make sure I have everything that I need to do this. But Linda, let's go back to the whiteboard now. But we're following along on this one. And if this is available to the students, they can look at this too. And I don't think it was that I didn't make it available to you. I think it was that it wasn't in the physics tab.
Yeah,
Okay,
I just didn't
so
find
anyway,
it. It's in the syllabus tab.
yeah, okay. So that's where you guys could look. Okay, so I'm just going to start writing some things here then again. And I probably have to pick my color again to make this happen. Okay, and I'm going to be doing this, pretty slowly. So this is going to be beta 1 minus beta 2 is equal to. Now, you see at beta 1, and I think actually the bird problem, they were going beta 2. It is so much easier to do this in a classroom. Okay, so I'm making that into a 2 and this one into a 1, which is the way I think it is on the slide that I'm not looking at right now. Okay, so this is beta 2 minus beta 1. Okay, so this is equal to, now I'm going to use that equation that we have. And so you see that is 10 dB. But then this is times, this is going to be the log of I2 over I0 minus, and still in parentheses, the log of I1 over I0, and then I'm closing my parentheses. Now, what you should recognize then is I did use the distributive property of multiplication over addition, because you see beta 2 is log base 10, beta 2 is 10 dB log I2 over I0. And then beta 1 is 10 dB times log I1 over I0. Okay, so this is the first line that we have on Linda's chart. Okay, so Linda, if you can go back and just show them that first line again, and I'm hoping maybe they're looking at it, but that's what's the first line, that it says beta 2 minus beta 1 is 10 dB, parentheses, log, and that is I2 divided by I0 minus log, and this is of I1 divided by I0. Okay, I hope people are good with that. Now what we're going to do is we're going to use a property of logarithms. And the property of logarithm that we're going to use is that the logarithm of a quotient is the difference of the logs. So Linda, let's go back to the whiteboard, please. And I'm going to annotate this a little bit more. So this thing, and I have to get the pencil again before I can do anything here. Okay, so this thing right there is log of I2 minus log of I0. Then we have this minus sign right there. And then we're going to have this thing, a property of logarithms, is this is log of I1 minus log of I0. So I'm going to erase this, and I'm going to rewrite what we now have for the next equal line. And so this is going to be the eraser again. And actually, I'm going to erase the whole thing because I can do that. So I'm erasing the whole thing, and it is like this. So now I'm still doing the equal sign. So this is equal to, and of course I have to go get the pen again. I'm going to stop telling you that that's what I'm doing, but that's what I have to do all the time. So this is equal to, and this is going to be the 10 is out here, and that is 10 dB. But now I have log of, this is I2 minus log of I0. And then there's a minus sign here, and this is a big minus sign. I'm going to put parentheses around that, and that's put another parentheses there. So then this is minus, but it's minus the other log, and so this is going to be parentheses log of I1 minus log of I0. And that's a property of logarithms, and that's I0, that last thing that I wrote. Now, Linda, would you be willing to have a go at explaining? And by the way, it's okay if you say no. I get that. But sometimes I think you do a really good job. Well, you always do a really good job of explaining things. And I think students want to realize, because what's really going to happen is that first term, that first expression has a minus log of I0, and the second has a minus times a minus log of I0. And so those are going to cancel out. I don't know, Linda, if you thought I did a good enough job of explaining that, or you want to say more.
I mean, that pretty much covers it. For the majority of this problem, then I really just want to emphasize to everyone, keeping track of the negatives is going to be a big piece of it. So making sure that you get the order correct. If you do the beta sub 2 minus beta sub 1, then that's fine. But you need to make sure that you're doing your log of I sub 2 minus the log of I sub 1. So just making sure that you get the order correct. But it doesn't matter which order you put it in. You'll get the same answer either way. It just needs to be consistent.
Okay, so what I just made an argument for was that this log of I0 is going to cancel out. So this is going to cancel with this one. Okay, so now I'm going to erase this, and I'm going to write the next step in Linda's chart there, but I'm just going to write it here. So I'm going to erase all this. I've cleared the annotations, and so now I'm saying this is equal to I still have the 10 dB there. But then I have the log of I2 minus the log of I1. But I said previously that the log of a quotient is the difference of the logs. That also means the difference of the logs is the log of the quotient. So you see, I can change this to be log of, and this now is I2 over I1. So see, we're doing some simplification here significantly, okay? And so that, and again, this all started out being beta 2 minus beta 1. Are we okay to this step, or do you have questions you want to ask on this step. I'm going to pause for a count of 10, Mississippi, because the next step is going to be pulling out that other equation that we have, which is I is equal to the power P divided by 4 pi R1 squared. Okay, hopefully everybody's writing this down, or at least looking at Linda's chart where you have this, because you actually have to do some of this to solve those problems. Now I'm going to erase this, but what I'm going to do is I'm going to put what I2 is and what I1 is into this equation. So I'm going to erase it, and I'm going to have another equal sign. Okay, so that is good. And so what we're going to have here then is, this is equal to, it is 10 dB. And then this is going to be the log. And now I'm going to put what I2 was and what I1 was. But an important thing for you all to remember is it's the same bird, so it's the same power. Okay, so the power at top, the intensity is, this is the power divided by, this is 4 pi, and that was I2, so this is R2 squared. Okay, so we have the power over 4 pi R2 squared, and that's divided by the I1, which is the same bird, the same power, and this is divided by 4 pi, and this is R1 squared. And this is a big, I think I'm going to erase this. We'll see if that works well to do that. I'm going to try to erase that piece and erase that piece, and that's not working so good. But then I'm going to put a big old parentheses around this to make sure that people understand what I'm talking about. And so this is the argument of the logarithm. So you have a complicated looking fraction there. I'm going to pause just for a count of 5, Mississippi, to see if anybody wants to ask about that. But what I'm going to do now is I'm going to cancel a whole bunch of things. Okay? Because that fraction, if I divide those fractions, it will cancel a whole bunch of things. You see the P, let's see, I need to get my pencil again. Pencil, there we go. So the P will cancel with the P. 4 pi will cancel with the 4 pi. Now everybody should realize when I canceled, there's really a 1 there and there's a 1 there. So that means what I have as a fraction is 1 over R2 squared divided by 1 over R1 squared. But if I simplify that fraction, 1 over R2 squared divided by 1 over R1 squared, I get something much simpler. But remember how you invert and multiply when you divide. So whenever I do this simplification fully, I'm going to have R1 squared on top and R2 squared on the bottom. So I'm going to erase this. Come on, there's the eraser. It's not doing a very good job. I'm going to erase the whole thing. Maybe that's cleaner. And now I'm going to the next step. And so the next step is okay, so we're going to say that this is equal to, I still have that 10 dB here, but now what I have is log of, and this is R1 squared over R2 squared. And that's the same thing as 10 dB. And this is log of, this is R1 over R2 whole squared. Now, the reason I'm doing this is I'm about ready to use another property of logarithms. And the other property of logarithms is if I have the logarithm of a raised to the x power, that's the same thing as x times, let's see, do I even have to do that? Well, I don't know if I'm going to do that or not. I'm going to just leave it this way right now. But remember that this is log base 10. But now we actually, and Linda, I'm sorry, but now we know, Linda, that one of these things is twice as far as the other, don't we?
Yes, we do.
And I think that R2 is further than R1. It's twice as far. So what I'm
That
going
is
to do, I'm going to erase, I'm going to try to erase R2, and I'm going to make that, so I'm going to write again. I'm going to write this, and this is going to be 2 R1 whole squared. Okay, so now you see what happens is the this is an R1 down here now, so the R1s cancel, and so what I have is that this is the log of 1 over 2 squared. So I'm going to erase this, and I'm going to write that as log of 1 over, and 2 squared is 4. So this is log of 1 over 4. So then I'm going back to erase all of this stuff. See, Linda, I did learn how to do that part anyway. Okay, so we're doing this. So this is equal to 10 dB. And this is the log of, and this is 1 over 4. Now I'm going to ask Linda to use her calculator and tell me what is the log of 1 over 4. And she may do that as 0.25. And Linda, I'll let you talk. You talk. Okay, now so Linda got, and by the way, that negative matters because that means that the intensity of the sound at point P2 is less than the intensity of the sound at point P1. And what we have is minus 0.602, and I'm going to leave it right there, minus 0.602. So now, Linda, let's go back to the whiteboard. Thank you. And so we're getting back to Linda's whiteboard. And so what we're going to do is we're going to take 10 dB times this, and Linda already figured out what this number was for us. It was minus 0.602. So 10 times minus 6.02 is equal to minus, and when we take 0.602 and we multiply it by 10, we get 6.02, and the units are dB. So what they said is if you are twice the distance, from the bird, one person could say that you are -6 dB in intensity level. Now, so that's the whole thing. We walked through it kind of step by step, but now we're going to go back and we're going to look at the whole thing in brilliant color and things like that. So I'm going to be erasing this just so we don't have that in the way. But Linda, let's go back now to the PowerPoint and we'll be looking at the PowerPoint. Okay, so you see we explained every line in this PowerPoint, and you see they get down to the last and it's -6.0 dB, and so that is the answer to this problem. And there is a reflection. It says the decibel scale is logarithmic. A factor of 2 in intensity corresponds to a 3 dB difference in the sound intensity. Okay, and we saw that because we were squaring things, it was even, it got down 6 dBs. Now, that actually is often on your certification exams. They will say, hey, a factor of 2 in intensity corresponds to what in dB? And the answer to that is 3 dB. Okay, now there is a practice problem down there that we could do, but this is, I think this really is a good example. Linda's dogs have paid attention to this problem because they hear something about a bird in the problem. But you should pay attention to this problem for other reasons, because this is very similar to one of your LSAs. And in fact, the LSA kind of says is, oh, gee, you're trying to hear some gossip, but you can't hear it very well because you've got a certain dB level. And so you want to sneak up closer so you can hear the gossip. And so how far do you have to go in order to have the gossip being told at a certain level? It's really the same kind of problem. Okay, so I'm going to pause here for a second and see if people have questions on this. And if they do, good. And if they don't, I guess that's okay too. And Amber, I am going to say something because I kind of answered a question you had earlier, and I hope you're still out there. We never know when on these Blackboard Ultra links. But I think what I clarified for you was how we're really talking about relative intensity, because we're looking at the ratio of I2 to I0 and I1 to I0. And then after we cancel things out, we're looking at the ratio of I2 to I1, and you can see that on the third step here in this equation. So Amber, I hope that made some sense for you, and maybe answer your question even a little more full.
Yeah, it's just a lot of steps, so I'm definitely gonna have to re-watch this a few times.
Well, and we're going to have, I think we're recording this, but also, I mean, I recorded this on my other video too, because this is like this is kind of this is a big step for some students because there's quite a bit going on. But this is something we're supposed to cover, and it involves the logarithms and everything else. Okay. Very good. Linda, why don't we go to the next slide? Oh, and this says we invite you to prove that a factor of 2 corresponds to 3 dB, and I would I'd encourage you to do that. But let's advance the slide again, Linda, and maybe I'll try my touch thing after this and do it. Okay, so now we come to a problem, and by the way, this problem doesn't involve logarithms, but it is from chapter 12. So I'm going to give you guys a few minutes to do this. And Linda, before you do depart, I want to make sure that I'm in control of whatever we have here, about showing it. And I don't know if, do I automatically have control? If you just ran away from the screen, would I be able to just do things?
It would stay with whatever is currently on the slide. So if the PowerPoint is up, then it should stay up.
Okay, but here's what I'm saying. Okay, let's pretend you left right now. And again, I know you're going to be here for just a little bit longer, but if you left right now, I could advance the slide and I could share my screen and we could do all those things back and forth.
I believe so. If you go under the share content and then click on
Yeah.
share files, do you see the PowerPoint?
Hold on. I'm not seeing, I can go and get the PowerPoint from, I know where it is, so I can go and
Okay,
get
because
it.
there should be a little thing under it that says main room files. I currently have a couple PowerPoints listed there. So if you can
Okay,
see
well,
that, then you can already switch back and forth. Otherwise,
I
you
think
would
I'm
need
going
to
to be
upload
just,
it.
I think I'm going to be fine when you leave. But anyway, I'm asking everybody to give this problem a go. And I'm also telling you that you should be able to solve this problem. Now, that doesn't mean I'm mad at you or you're failing the course if you don't, but I think you should be able to solve this right now with things you know. And the things that we studied before was this is actually quite a bit like the range equation that we studied in ultrasound, and which definitely will be a problem on the final exam. So anyway, I'm saying this is mapping the ocean floor. The ocean floor is mapped by sending sound waves, sonar downward, and measuring the time it takes for their echo to return. Now, this is sonar, this is an ultrasound, so the frequencies are different, but the physics is very much the same. And so this is just like ultrasound. You send a sound wave down and it hits something and bounces back. And so what we're doing is you send it down, that's what the sonar does, sends the sound wave down, and it measures how long it takes to get the echo back. That's exactly what your transducer does. Now, from this information, the ocean depth can be calculated if one knows that, and this is a difference. Now, to tell you the truth, it's not a big difference. A lot of times we say in soft tissue, which is really a lot of water and body fluids, but in soft tissue, the speed of sound, ultrasound in soft tissue, and it doesn't matter what kind of sound it is 1,540 meters per second. That's the number we often use. And you use whatever number they tell you in the problem. But this one says that salt water, the speed of sound, is 1,531 meters per second in seawater. Now, seawater is salt water, but your body has salt in it too. So, you know, that number is really very, very close to what happens with ultrasound. But the distance is going to be very much different, though, because you're going down to the bottom of the ocean. And even though I have an enormous belly and things like that, the width of my belly is nowhere deep as the ocean. And so what happens is, you know, this is going to take a lot longer. When you're doing your ultrasound, and we talked about the 13 microsecond rule, 1 centimeter, the go return time for 1 centimeter is 13 microseconds. So it goes really fast and you're not really very deep when you're doing ultrasound. When you're going to the bottom ocean, it's deep. So anyway, here's the question that you should be able to work. If a ship sends out sonar pulses and records their echo 3.27 seconds later, how deep is the ocean floor at that point? And we're assuming that the speed of sound is the same at all depths in the water. Okay, everybody, give it a go. And Linda, how long would you speculate we should allow students to do this? And they're going to be using their calculators and
I'd
things
say
like that.
3 minutes.
Okay, so we're 3 minutes, and Linda's going to be here, I think, for maybe at least 3 more minutes. So Linda, if you can kind of clock that, that would be good. And then we'll go through the solution. But consider this is a little bit of a test for you. Do you know how to do it? Think about it and come up with a solution. And I hope you're motivated to try to come up with a solution because, you know, I'm probably going to ask a range equation problem on the final exam on the physics part. And so, it's going to be similar to this problem. So everybody is working on this, and Linda's going to let us know when time expires.
All right, they should be just about good now.
Okay, good. Okay, so what I'm going to do is I'm going to try to write on this, Linda. I don't have very much space. My finger is chubby, but we'll just see. Okay, so distance is equal to velocity times time. So what we're doing is we're saying, well, so velocity was 1531 meters per second times, and the time was 3.27 seconds. So you see the answer is going to be in meters, and if I multiply those two numbers together, I will get approximately 5,006 meters. Now 5,006 meters, but now I'm going to ask you, what is the answer to the question? And the answer to the question is 2.5 kilometers. Now, the reason it is 2.5 is, you see, in 3.27 seconds, it went down and it came back. So we learned when we multiplied these things together that it went a little bit over 5,000 meters, but that was the go and return times. So it went twice that distance. So instead of going 5,000 meters, it went down 2,500 meters, which is still pretty deep. And if we wrote that in kilometers, we'd write 2.5 kilometers. I'm going to pause now in case there's a question about that problem. This again is a very representative problem. In fact, both problems that we've talked about tonight are very representative problems. I expect both of them will be somehow represented on the final exam. Okay, I'm not hearing any questions, which is fine. Did you see that comment, Linda?
Yeah, so they're saying that when you multiply the 1,531, the 3.27, and then you divide that by 2, then you get 2,503 and change meters. So yeah, when you turn it into kilometers, you're moving the decimal place 3 places to the left. So that's how we end up with 2.5 kilometers.
And again, if you told me, oh, it's 2,500 kilometers, I certainly would count that right because you had the right thing there, but you should have units to
Well,
tell
it'd
me
be
what it is.
2,500 meters, right?
2,500 meters, yes, I'm sorry. 2,500 meters. Okay, now I'm going to try to erase the annotation. Yes, thank you, Linda. Good. Okay, so what I'm going to do is I'm going to erase the annotations on this, and I'm going to ask Linda to advance. And Linda, I know you're going to vanish sometime, but let's just go to the next slide. Now, this is a different kind of problem. You got to keep things straight, but this deals with human hearing. Okay, and this deals with another equation that we've talked about recently. Okay, so the human outer ear contains a cavity called the auditory canal. One end has the eardrum in it, and while the other opens to the outside. And they talk about how long it is. Let's see, actually, that's talking about harmonics, so we're not going to talk about that. Let's look at number 34. That's a better problem for us. Okay, whale communications. Blue whales communicate using a sound frequency of 17 hertz. Now, by the way, 17 hertz is a very low frequency. And in fact, we told you that humans can hear between 20 hertz and 20 kilohertz. But you see, this is too low. Most people would not be able to hear the whales doing this, but that can be heard 1,000 kilometers away. What is the wavelength of such a sound in seawater where the speed of sound is 1531 meters per second? Okay, now Linda, I'm going to try this right before you leave just to see if I can do it. Okay, so I'm going to go to, I'm going to share, and I'm going to share, oh, it does say share files. So if I hit that, that takes me back to that, so this should work. Okay, so I'm going to share a blank board here, and we're going to work this problem together. And this was problem number, I think it was 34, maybe. I will find it. And we had these swales and things like that. Okay, so I think it is problem 34. So here's what we need to do. Now, this is the equation you need to remember for this problem 34, that V, oops, I need to get my thing here. So there it is. I'm doing my drawing tool, and it's not showing me my, oh, I guess I need to go back like that. Okay, so now it's showing me my drawing tool, and now I can get to color, and I can do this. And Linda, thanks for all your help. Okay, so on this one, then, what we have is the formula that we talked about last time. And the formula that we talked about last time, there's a lot of ways we could do it, but we say lambda is equal to V over F. I told you this was really a fundamental formula, and it is. So the wavelength was what they asked us to find. Okay, so we know that the velocity was 1531, and the frequency was 17 hertz. Now let's talk about the units on this. This is meters per second, and hertz is really the same thing as 1 over seconds. So whenever you do this calculation, the seconds cancel, and you do get meters for the wavelength. So that is good. But the wavelength then is going to be 90 meters. Whenever you do that division, you get 90 meters. Okay, do we have questions or not? I'll count to 5 Mississippi, and if not, then we'll go back to the PowerPoint show, and we'll talk about some more problems here. Okay, I'm going to erase this, and I'm going to go back, and I am going to go to try to do the shared files. And one of these files was tonight's file, this one. And so I'm sharing it now. And I think what we'll come up with is select a slide to begin sharing. Okay, this is not the slide we want. I need to go up a little bit to find the slide. Those are important examples we're going over tonight. Okay, we did that problem, and we just did this problem about the whales. Now, I'm going to read a problem about the dolphin clicks. One type of sound that dolphins emit is a sharp click of wavelength 1.5 centimeters in the ocean. Now, this means that dolphins and whales probably don't communicate very well, because the whales had something that was 90 meters long was the wavelength of their communication. And here we have, for dolphins, the wavelength is only 1.5 centimeters. It's not even a meter. It's just a small fraction of a meter. So then the question is, what is the frequency of such clicks? Okay, so what we're going to do is we're going to do this, and we're going to see that, oh, we get to use the same equation again. So what I'm going to do is I'm going to share. See, do I have to stop sharing? Okay, I'm sharing again. Okay, and I wanted to go to the whiteboard, and it's not letting me go to the whiteboard, so I guess I'll just write on top of this slide. Now, this time, this is B, and so what we want to have this time is we're solving for frequency. And we know that frequency is equal to the velocity over wavelength. So that's velocity over lambda. And I'm going to ask Amber, because I think she's still there. Can you see me writing?
Yeah.
Okay, now I know this isn't ideal, but we just take these numbers then, you see. And what they wanted us to find is, they wanted us to find the frequency. So the velocity was, in the numerator, I put 1531. In the denominator, I put, and you got to be a little bit careful about this, because the unit in the numerator is meters per second. But in the denominator, they told us this was in centimeters. So we have to be careful about that. And so we're going to adjust it. So I have to make this cancel, I have to use meters. So centimeters, it was 1.5 centimeters. So that is 0.015 meters. Now, everybody notice that what I did was I changed centimeters to meters, because I had to do this to get my power of 10 right. But now what will happen is the meters will cancel with the meters. My answer will be in reciprocal seconds. And I need to draw this again. Okay, so my answer will be in reciprocal seconds, which is hertz. And so when you pound that into your calculator, you should get 102, and my notes here say kilohertz, but that's 102,000 hertz. Now I'm going to pause for a moment or two in case somebody has a question about that. Okay, we're going to go to part C. Now I'm going to erase all those annotations so we can see part C on this problem. Okay, so part C says dog whistles. One brand of dog whistles claims a frequency of 25 kilohertz. Now, by the way, 25 kilohertz is higher than almost any human can hear. But you see, your dog can hear that, but you can't. So you could be signaling your dog without bothering the neighbors and things like that. So it's 25 kilohertz for its product. And again, you have to think about that being kilohertz. So then the question is, what is the wavelength of this whistle? Now, you need a piece of information to do this, and that has to be, what is the speed of sound in air? Now, the speed of sound depends on the medium. So the speed of sound in air is one number. The speed of sound in soft tissue is another. And in fact, it's much faster in soft tissue. So anyway, we're going to be using the same equation for this. We're going to be saying that lambda, let's see, I need to make it bigger. I have to be jumping things around here a little bit to make this work. Okay, so lambda, again, is equal to V over F, but V this time is 344 meters per second, and this was 25 kilohertz, so this is 25 times 10 cubed hertz, and that's 1 over seconds. So the seconds cancel, and you do get meters. And if you do this, what you will get is that the units are going to be, this is problem C, it is going to be 0.014 meters or 1.4 centimeters. Okay, Monica asked, where did the 344 come from? Well, you see, if you're whistling for your dog, you're doing it in the backyard. You're not doing it underwater. And so you see, sound is different depending on what's the medium. So if I'm whistling in the air, there is one speed of sound. And by the way, we've done this 344 before in this class. We've done other problems where we had that. But we also, earlier tonight, have done soft tissue or seawater problems where it was 1531 meters per second. So you see, sound travels faster through soft tissue in your body than it does through the air. And the reason is that the molecules are jammed closer and closer together. So the 344 was something that you kind of had to know to do this problem, but also we've done that in problems before, but I did tell you what that is. But you see, again, there's a good takeaway here that the speed of sound is different depending on what medium you're going through. So Monica, that's my best answer on that one. Okay. Now we're going to do another problem. I'm going to erase this. Okay, so we talked about dolphins, we talked about whales, we talked about dogs. Now we're going to talk about D, and D is about bats. Okay, while bats emit a wide variety of sounds, one type emits pulses of sound having a frequency between 39 kilohertz and 78 kilohertz. What is the range of wavelengths of this sound? And the next problem we're going to do is having to do with ultrasounds. And in fact, I think I'm going to not talk about the bats. I'm going to talk about sonograms. So I'm going to part E, and we're going to do part E before we adjourn tonight. And actually, let's see. There's part E, and I guess that's the last one. But anyway, this is fine. Okay, ultrasound, which is what you guys study. And by the way, ultrasound, I know I said this before, but this is a exam question on your certification. Ultrasound is any sound waves that are above 20 kilohertz. so people can't hear them. So you have real fast ultrasound, you have slower ultrasound, but that's called ultrasound. It's a frequency above 20 kilohertz. Okay, so ultrasound is used to view the interior of the body. That's what you guys are about. And it says, much as X-rays are utilized. It's really a different technology, though. X-rays are light rays, and they have different safety factors and things like that. Anyway, for sharp imagery, and by the way, I've asked a question like this. Actually, I have asked exactly this question on an exam before. For sharp images, which is what you want, the wavelength of the sound should be around 1/4 or less the size of the object being viewed. Approximately what frequency of sound is needed to produce a clear image of a tumor that is 1 millimeter across if the speed of sound in soft tissue is 1550 meters per second? I'm going to give you a minute to think about this and think about how could you do this, because honest to God, this has been a full problem on my final exams before, is exactly this statement. Okay, so everybody think about that for a minute. I'll give you a minute to think, and then I'll come back. I am watching the time for us. We're in good shape to finish this problem. But everybody think about, okay, how would you do this problem? Okay, well, the wavelength should be, and it says it could be even less, but you want the wavelength to be less than, let's see, I need to go and get my thing again. So the wavelength has to be less than 1/4, and let's just say, what is it when it is 1/4? So we're saying lambda has to be 1/4 the size of the tumor that we're trying to be measuring. And the tumor was 1 millimeter. So that means that lambda had to be, and that's 0.25, had to be 0.25 millimeters. But that wasn't the question that they asked. They asked is, what needs to be the frequency of the ultrasound? So I'm going to erase this, but we're going to remember that lambda had to be this in millimeters. Okay, so I'm erasing this whole thing, and we'll continue the problem then. So we know that lambda, let's see, we know that lambda is equal to V over F. I hope you guys are realizing the same equations come over and over and over again. And this was 0.25, and that was millimeters. And that's equal to the speed of this. And by the way, Monica, this time we're going through soft tissue because you're doing ultrasound. And I think they told us to use 1550. So I put 1550, and that is meters per second. 1550 meters per second. I said, well, Jim, do I have to be careful about these units? Well, damn straight you do, because one of them is millimeters and the other one is meters. So you do have to know how to deal with this. But that is the velocity divided by the frequency. So I have to solve this for what is F. And again, so whenever you're studying and looking over this video or things like that, you want to say, okay, so how would I do that? Well, what you're going to do is you would multiply both sides by F and then divide by the 0.25 millimeters, but you'd have to change millimeters to meters or vice versa, so they would cancel out. And so I encourage you to make sure that you can do that calculation. But what will happen is, if you do that calculation, what you would get is that this has to be, and I'll go get the thing again. This has to be 6.2 megahertz or higher. So that was a physics final exam question that I've asked before. And again, you have to have the units right and everything to get full credit. But that's what we've got. So you see again and again and again, we're seeing the same equations are getting used. Now I'm going to erase this. I do know what time it is, but I want you guys to get your money's worth. I'm teaching the best course I know how. So we're advancing this slide and we're going to another one. Now, oh, by the way, this number 40 down there is one of your LSAs. I'm just going to read it and you can think about it. It's called eavesdropping. You are trying to overhear a juicy conversation, but from your distance of, that looks like that's 15.0 meters away, it sounds like only an average whisper of 20.0 dB. That's the intensity level that you're hearing. And you are not comfortable just hearing the whispering. You want to really hear what's going on with the gossip. So you decide to move closer to get the conversation at a sound level of 60.0 dB instead. How close would you have to come? So you see, this is very much related to the bird problem that we did, but it's asking a different question, and that's an LSA. I think tonight was a good night. We were able to cover things despite the technical difficulties. We talked about the important bird problem. We talked about the lambda equal V over F equation again. And so we're covering stuff that definitely is important stuff. And so I hope it's going well. I will do office hours later. I hope to be doing my regular PC upstairs. I'm going to go upstairs and see if I can make it work. And I have to figure out how to turn off my daughter's PC too. Okay, so everyone, please be careful, and I will maybe see some of you sometime soon. Bye-bye. Good night. And I'm going to stop the recording.